Moving on to the box and whiskers graph then, or box plot graph. So this shows the total range, the interquartile range, the medium, the upper quartile and lower quartile. So in this case, the X's or crosses on here is the median. The upper, the line at the top of the box plot will show the highest value, and the line at the bottom will show the lowest value. Therefore, you can determine the range from this. You can also determine the middle 50% of the data through the shaded box in the middle. So the blue box, as it would be, is the middle 50% of that data, and the red box that is shaded in is the middle 50% of that data. So on figure 15, you can see that the blue box represents systolic blood pressure and the red box represents resting heart rate. And you can see again it's titled, the title of this is the blood pressure test results. It's literally just showing the results. It's fairly descriptive. So calculation of the upper quartile, lower quartile and interquartile range will actually be discussed later on when discussing statistics, so descriptive statistics. So obviously this is just the presentation of those statistics at the moment, but how to actually calculate those statistics will be discussed later on. Of course, the trouble with these box and whiskers graphs is that it's very difficult to distinguish outliers. You could have a really high value at the top, and then all of the rest of the data is concentrated below that. It's not the easiest to distinguish with these graphs, whereas with scatter plot graphs, for example, you can easily distinguish outliers through the individual scores that are shown, whereas all of the scores in box and whiskers graphs are kind of grouped together. We move on to histograms then. So histograms basically show the spread of continuous data. This is kind of focused in on frequency. So you can see in figure 16 that the title of this histogram is the frequency of standing vertical jump test scores. So you can see that it's grouped together, so groups of intervals of 5. So you've got the first group is 15 to 20, 20 to 25, so on. And then you have the frequency shown as well. So the frequency is basically just stating how many scores are in that 15 to 20 category, in that 20 to 25 category, and so on. So for the first bar, you can see that there are 6 values in that 15 to 20 category. There is 1 value in the 20 to 25 category, 4 values in the 35 to 40 category, and so on. It basically establishes how frequent those groupings are, how many values are in those groupings. It's something that is kind of almost essential for values that involve continuous data, because it's much harder to single out values that are decimal places and have data displayed on a graph for each individual value, whereas if you group those values together, it's a bit easier to establish a visually aesthetic graph, because you don't have loads and loads of individual values. It makes it more concentrated and more grouped together. Obviously, histograms are key for continuous data, but you might want to use maybe bar charts for nominal data or ordinal data. Continuous data generally is better off presented in histograms for the reasons previously explained, that it's much easier to group things together when you have those difficult decimal numbers. It's easier to put them into those bins. Histograms are basically a kind of foundation for the normal distribution curve. So the normal distribution curve can be seen here. So what a normal distribution curve is, it's basically a probability distribution. So the proportion of the area that falls under the curve between 2 points on a probability distribution plot, it basically indicates the probability that a value will fall in that interval or in that area. It's basically a theoretical curve that shows how often an experiment or test will produce a particular result. The curve's obviously meant to be symmetrical and bell-shaped, which would imply that the results would usually be near the average, but will occasionally deviate outside of that. These deviations are what we previously mentioned to be standard deviation. Now, standard deviation is kind of a number expressing by how much the members of a group differ from the mean value for the group. And this can be shown here on this graph. So you can see at the bottom of figure 17 the 0, +1 and -1. And those are standard deviations at the bottom. So that's one standard deviation, and then the +2, -2 is 2 standard deviations. Now this can be assessed through percentages. So one standard deviation is, +1 standard deviation is 34.13%, approximately, which is just over a third of the data. So that is implying that just over a third of the data should be within that +1 standard deviation. You can see at the top of the graph that there's that 68.26%. So that's implying that approximately 2/3 of the data should be ±1 standard deviation. So 68.26% of the values should be within that percentage from the mean. And then as you go further out on the bell-shaped curve, you can see that the percentages are smaller, saying that there's a smaller amount of values that deviate further away from that mean value. So there's a higher concentration, or in a normal distribution there should be a higher concentration of values closer towards that mean as opposed to further away. How narrow or wide that bell is, as long as it's symmetrical, it's still that normal distribution. But if you have a more narrow bell shape, this generally means that your values are closer to the mean, so you might have a higher percentage of values closer to that mean, therefore less of a standard deviation, a smaller standard deviation, whereas a wider bell-shaped curve would have a larger standard deviation, as there are more values deviating from that mean value. This is where we relate back to histograms, because you can see on this histogram in figure 16 that there isn't a normal distribution because it doesn't have that bell shape. That initial first bar kind of eliminates that possibility. Had there been that bell shape, perhaps if those the third and fourth column had been at a 3 as well, and that first column had been a 1 in terms of frequency, then it would have been that bell-shaped curve, and we could have called that a normal distribution curve. So that's the normal distribution curve, but you also have asymmetrical distribution curves. So this is where the curve skews. It's still kind of that kind of almost a bell shape, but there's actually a skew towards one side. So the direction of this skew explains whether it's a positive or negative skew. This could potentially be due to outliers, which on figure 18 you can see as the cross or X. But it basically is where the mean, median, and mode are not of the same value. So you can see in figure 18 that the distribution curve on the left is a negative skew, and the distribution curve on the right is a positive skew. The negative skew occurs where the mean is further to the left than the median and the mode, and the positive skew shows the opposite of that. Like I said, this is usually due to outliers that are affecting the data and therefore affecting the median and the mode. So there's a way to deal with that, a way to deal with outliers, and that is trimming and Winsorizing. So an outlier is basically just a value that doesn't fit with the trend of the rest of the data. It might be that you have a set of data which is all single digit values, and then you suddenly have a value that is 100. It therefore doesn't fit with the trend of that data. It doesn't fit with the rest of the data, which can affect those descriptive values, such as median and mode, like previously mentioned. So yeah, obviously your median is going to be completely different if you have an outlier, because if you had a selection of numbers 1 to 5, your median would be fairly close to those other numbers because they're all quite close together. Whereas if you had 1 to 5 and then suddenly just a random 100, your median is going to be very different as a result of that 100. Similarly, your range would be much larger as a result, which is why some people would like to discount outliers and use trimming and Winsorizing. So both eradicate the effect of outliers. Trimming is basically just removing the outlier as a whole from your data and just using the rest. So you can see that we've eliminated 54 here. And Winsorizing is where you change the outlier to match the data. So you basically reduce it or increase it so it's similar to the data. So obviously you can see here the highest value that doesn't include the outlier was 7. So you've reduced the outlier down to 7 so that it is closer to the data. Now you wouldn't make 54 just any random number because it's obviously a high number, so you would go with the highest number that you have there that would relate closely to the data.